Let's start. Today I'm going to share the main details from the fourth chapter towards the calculus of redundancy, and also to share some ideas of how can we use this theoretical approach in the future. Because I suppose that this uh, theoretical base has a more potential for its further practical implementation. First of all, I would like to start with the time when Leydesdorff and Henry Iskowitz proposed their theory of triple helix model, and at that time the question arose how to measure the effectiveness of this system, of this model. And Loet proposed to exploit Shannon-based information theoretical approach to measure synergy. And synergy is generated in this central overlapping area. But when we look at these two diagrams, double helix model and triple helix model, we can find the things that if we base on the information theory proposed by Shannon, we have some problem. This problem is called sign change problem, because for the double helix model, we have to subtract this overlapping area in order not to count it twice. But in triple helix model, we have to add this overlapping area, and it means that we add additional uncertainty to the total uncertainty. And that's why we can't count with Shannon type information. And Loet called it configurational information. But actually, this puzzle wasn't solved until the recent time. And it was pretty much a very big obstacle. And then Loet proposed the way of how we can solve this problem by adding the positive interaction. And when we add the positive interaction, we won't have this problem further. And this positive interaction was called as redundancy. And it's positive for all the cases, for all type of the systems, with even number of actors and uneven number of actors. Actually, by introducing this positive interaction, we add excess information value, and we could consider redundancy as additional information, additional options, and additional opportunities. From the mathematical point of view, it's pretty much not easy to explain the logic, but we can explain this logic from the social perspectives and some technical perspective as well. For example, if you look at this picture, this is light source intensity, and we can consider the light source intensity for two cases, for non-coherent light sources and coherent light sources. And light intensity for the coherent light sources will be pretty much higher rather than light intensity for the non-coherent light sources. We can make some bridge between this theoretical description and the things that we have in the nature. In order to make it more clear, I put this scheme here on the slide, and at the base A, we can see how information is transmitted from the information source to the destination according to the logic of Shannon's theory. But we were considering this approach added some minor additions, so-called minor additions. He added semantic noise box and semantic receiver box. And at this level, at level B, the redundancy is generated actually, and the meaning is conveyed. But at level C, the received meaning can affect behavior of the actors. So we can understand the same information in different ways according to our communicational codes. And each of us has our own communicational codes. That's why the same information could be understood in different ways. It's like on this picture, we have a plant and different animals. And these different animals consider this plant in different ways. It depends on their own enzymes. All of them has its own enzymes and they're totally different. So in order to connect redundancy and meaning, I would like to talk about this technical things and consider Betterson's position. He noted that the concept of redundancy is a partial synonym of meaning. And Shannon defined information as probabilistic entropy. On this picture, we can see that there is a maximum entropy and observed entropy. As we know from the second law of thermodynamics, entropy is increasing over time. And the redundancy is the difference between maximum entropy and observed entropy. And it's crucial for the technical systems historically realized. But for social systems, self-organizing systems, there are another obstacle technologically made feasible. What does it mean? It means that system is able to add new options without necessarily realizing them. And we can keep options in mind, and impossible options could be made possible because of cultural and technological evolutions, thanks to technological progress. That's why for social systems, we can have rather higher redundancy, measure for redundancy than for the technical ones. And the speed of increasing redundancy for social systems is rather higher than the speed for increasing redundancy for historical systems. We can see the changes of redundancy increase here on this picture. This picture represents triadic closure, so-called triadic closure, and we can see different types of rotations. Clockwise rotation and counterclockwise rotation. The first one is about traditional systems historically realized, and the next one is for self-organizing systems. And redundancy is the difference in these two vectors. It's a scalar value. So I would like to sum up the basic ideas. First of all, we have to pay attention to the weavers editions.
¿Lo puedes poner en el tuyo mejor?
Sí.
Sorry.
Sí, puedo.
That the Shannon model of communication was extended with Weaver's levels B and C. And The second one is about redundancy that can be generated and interfaces among sets of relations which are structured by codes, thanks to the different communicational codes. And the third one, the extension of Shannon's information by the theory of meaning and knowledge generation. Adding to this third summary, I would like to share one idea that one can show that redundancy approach is a cornerstone for the further development of the theory of meaning. And here you can see on two graphs. The first one is the financial market as a price movement. And the second one is COVID-19 epidemic spread. In days for the United States, starting from the first case. And we can see that the approximation line or received from the redundancy probability density function is pretty much closer to the real data. It gives us a base that we can use the theoretical approach further and develop it further and try to create the critical to make critical experiment and to look at the data in some other different spheres. Here, in order to be in time, I would like to finish my presentation. If you have any questions, I will be happy to discuss. Thank you.